going to be like a boss at interpreting titration curves, so it's going to be something that's quite easy to get in 30 seconds or less or so on a multiple choice question. Chase or Miriam, give me one difference that you can see or note on a titration curve. That's the difference between this one and this one. Excuse me? A weak acid. So if you have a titration curve for a weak acid, strong base versus a strong acid, strong base, it's starting off at a higher pH. Why? Coming into solution, right? So we're going to start up maybe at 3 or 4, whereas a strong acid, so basically when you say this, you're saying that the weak acid starts higher, so you're saying the strong acid starts lower, like down here at 1. Okay? Jade and Fatima, tell me something more. It's got like a little loop, a little curl at the top, so instead of being a straight kind of up and to the right, it's going to have like this little bit of a hump. And this one's going to start straight. Okay? The hump's not very good, but it's there. Okay? Gigi and Joy? So shorter vertical section. Okay? So I'm going to kind of finish this part out. Okay, so that's a short vertical section. So you're saying this one has a longer vertical section. Okay? So that's another one. Cassie and Julian, tell me something else. It's pretty obvious when you're looking at it now, but I just need you to say it out loud. Okay, so the strong base, so that's actually not what I'm thinking of, but yeah, that's good. So after the equivalence point, the strong base is in excess, and so they should be ending up identical at the end, assuming we have identical conditions like molarities and volumes, of course. So because the strong base is then the only thing present to control the pH, they should have a similar curve on the backside. One more obvious trait. What about the equivalence point? This is going to be what? Well, you're right, say less, but what, I mean, we should know what this one is. Strong acid, strong base should be 7, 8 or 9, right? So it's kind of in the middle of the vertical section. So it could be 8 or 9, kind of depending exactly what we're dealing with. All right, so there's like very key differences. The loop thing at the beginning, the pH initial, the pH of the equivalence point, and then the general shape of the graph. So there's one important piece more. Does this curve show any indication of a buffer?
No.
Why? Wait.
Because the strong acid dissociates completely.
Okay, so we just know that strong acids ionize completely, so we know this is not going to form a buffer, but why is this curve not indicative of a buffer? Are you seeing any like, well, this one's a little bit misleading maybe, but do you see any like very slow change in pH where it's like a buffering region? No? I mean, this is staying constant because you have a severely limited amount of strong base being added, but then it jumps quite high very quickly, whereas this one has a buffering region, and that the buffer region is supposed to be where in this case, weak acid is making what? It's conjugate base, and so there's this constant fight on trying to fight the pH incline, and so that's why it has like a slow incline there. And then you end up with, after all, that slope causes this short vertical section. Okay, so we are finally going to check 1 through 6 on buffers, or problems with buffers, and then we're going to kind of go through some more titration steps, okay? So overall, though, we're going to do some upfront work with titrations, and then we're going to work on our pre-lab or our buffer lab tomorrow. Okay, so we have some groups that some people I need to talk to you about that. Okay, so let me scroll back, and I've already talked about a couple of these, and I highlighted the most important parts because I wrote paragraphs, mainly because I want it to be super elaborate. So when I upload this, you'll have more information, but for the time being, let's just look at the highlighted sections. So I've talked to a couple of videos about this one already. If you have ammonium chloride and you want to make a buffer, you simply need what? Ammonia, right? There's 2 ways to make that happen. literally add the weak base ammonia, or I could do what with this? Add a strong base to make ammonium, well, I don't have that written down, ammonium undergo partial neutralization to make ammonia and water. So there are two ways to do that, direct addition or partial neutralization. Whenever you add a strong amount of, or a small amount of strong base, this is your reaction. You know that your pH should do what? If you're adding strong base? Increase, okay? And that's simply because you're adding a little strong base and you're taking away the conjugate acid through that reaction and you're making ammonia. If you dilute the buffer, if the dilution process does not change the ratio of the weak base and the conjugate acid, what happens to pH? It stays the same. So we know the relationship now. pH is based on this relationship in the Henderson-Hasselbalch equation, as well as like what you're dealing with. But if this ratio changes, it will shift the pH one way or the other. And this one you guys had to, what do you have to do? Solve for hydronium. Okay, so you had, it said equimol, or equivolumes, equal volumes. So I just made up 1 liter and 1 liter because you can work with 1 liter really well. And since in this case you technically have a buffer, but many of us probably set up an icebox first to see the relationships we have. So 0.05 moles divided by my total of 2 liters, 0.02 moles divided by my total of 2 liters, and then go through ice, and you end up with, as you set up in your Ka expression, hydronium times hypochlorite over hypochlorous acid, plugging in your values, the molarity values, of course, because iceboxes are going to use molarities, equal to the Ka value itself, and neglecting X, so we should have had no change from initial to equilibrium, assumingly. Our hydronium should be 7.75 times 10 to the negative 8th, and that was small enough to neglect. So then that was going to give you the opportunity to find pH. What was another way to approach this? Henderson-Hasselbalch. So many times, like we're getting in the groove, like we're figuring out, oh, I can use Henderson-Hasselbalch when I have a buffer. But you have to recognize you have a buffer first. But this is your backup plan. It will work. It's just more long-winded. Okay? And 3, we had a buffer. Henderson-Hasselbalch. It's repetitive. I'm sorry. Okay? So 3.92, as long as you're setting up your Henderson-Hasselbalch with this was a acid, so you used your Ka conjugate base over the weak acid, setting up everything with the correct numbers in the correct places, you should be fine. So they gave you moles and moles, so 0.6 moles and 0.4 moles. Remember, you can plug moles into Henderson-Hasselbalch, no problem. We talked about 4 yesterday orally, so I'm skipping 4. Carla 1, we talked about that. So in 5, this is actually where more folks had some questions. You had just to set up your K expression. So this is a weird acid, but the acid has an H in the front, donates to make azide and hydronium. So when you set this up, this Ka is equal to blah blah, your products over your reactants. And after that, it gave you some initial values of volume and molarity, and it said to find hydroxide. Is that this one? No, find pH, right? So looking back at the setup of Ka, many times things build, right? So like if I have this Ka and I want to solve for pH, which piece of this Ka do I really need to solve for? The H plus, right? The hydronium. I can technically do that. It just takes a little bit more time. So I've shown you this here to show you that if you get in this route, don't stop. Like you can totally do it through Kas and ice boxes and determining from the initial setup with your K expression, you can plug in data and you will get pH. It's just a little bit longer method. So given the volume and molarities, going to moles of the acid and the, I think I wrote one of those backwards, but there's your acid of 0.0075 moles and your azide, sodium azide of 0.0123 moles. technically those are moles, so you got to get some molarity before you plug into your K expression. But if you go through the whole process and you plug into your K expression, but of course rearrange the K expression to solve for the thing that will help you resolve pH, plugging in each of these values, you end up with your hydronium is 1.7 times 10 to the negative fifth, pH it, and you get 7.77 or 4.77. But that is a longer route, but it is very doable. So don't, like, you have many ways to solve some of these problems. This is the route I would take. Just plug into Henderson-Hasselbalch. Because your Ka was already established in part A. Your moles of sodium azide, you had to calculate yourself because it was given to you in grams. And your moles of the acid, you have to calculate yourself because it was given to you in molarity. But that's so much easier. Okay? And you end up with the same answer. Questions right here? Yeah.
Did you not do like the concentration of these items?
Yeah. Yeah, so that's what I'm saying. I had like found moles earlier, so I just went ahead and plugged in moles. But again, Henderson-Hasselbalch is flexible. Moles or molarity, you just have to make sure they're in the same net volume, because once they're put in the same container, they're then in the same volume, so make sure your molarities are correct. So then for the last part of this one, which is kind of what we were referencing yesterday, because we were talking about partial neutralization. Oh, but this one's not partial. This one was talking about, you had 150 liters or 150 milliliters and then 75 milliliters, but with respect to both of these, they ended up with the same moles. So you have the same moles of the weak acid and the strong base. So since we have equal moles acid and base, where are we at in our titration? The equivalence point, right? So this is the key point from one of your videos on titrations. When you're at the equivalence point, there's only one thing that controls the pH. Is that what, say again? Not water. Conjugate of what? In this case, the weak acid, right? So in this case, and this is small for the two sides of the paper, you have the weak acid and the strong base being added together in an equimolar amount. So they're both limiting, they're wiped out. So you have water and technically sodium azide, Na(N3). So you have a salt. The salt is the only thing that controls the pH at the equivalence point. But you can't just say, hey, the salt's, basic because it comes from a strong base and weak acid. You can literally not say that. Okay, you can think it because it helps guide you in your predictions, but you cannot say that. You actually have to say the conjugate. What's in 3 minus? Conjugate base, right, from this weak acid. The conjugate base is going to undergo salt hydrolysis, and then we're going to do an ice box. So I kind of put step 1 and step 2 because now I'm in, I was in a BDA format initially because we're in moles, but once you run through salt hydrolysis, it's an equilibrium. So this isn't technically my mini version of an ice box. So you had 0.0075 moles from the 2 reactants making your single product over here, but I divide by 225 milliliters. So where did you get that from? Or where can you get that from? The total what? Total volume, right? So you had 150 mils and then 75 mils, which gives you 0.225 liters. That's an essential step. Most people forget to go from moles to molarity. But once you set up your ice box and you have your molarity, minus x plus x plus x, that's the molarity, 0.033 continued equal to Kb, because how is azide working here? How's it behaving? As a base, right? It's taking the H back from water to make OH minus and this azidic acid or whatever this is. So it's acting as a base. So you have a Ka from this acid, like way up in part A. So then Kw over Ka gives you Kb. That is the part that most people forget too. So I'm seeing some non-quizzes, but you guys are getting a lot better. So keep making progress. What's up?
Isn't it 0.033?
I think that's 0.033. I'd have to go back and check my math here. But take 0.0075 divided by 0.225. Somebody. 0.0075 divided by 0.225 for me. 0.33. I'm hoping this all is right. Please double check this for me. I hope not. Butterfingers up here, but just check this. So this is your KB, x squared over 0.0333 times your KB, solve for x. That's right, okay, good. That's just me writing. And then that's your hydroxide, and then we were done. It didn't even ask for sulfur pH. It just said sulfur hydroxide. But basically, the point where we get kind of really long-winded is if you have a titration, you're at the equivalence point. Who controls the pH at the equivalence point? The conjugate of this salt, right? So some part of the salt is going to be the primary ion that reacts with water through salt hydrolysis. But we can't just take the Ka or Kb as is, what must we do? Like we can't take the acid's Ka or we can't take the base's Kb. We have to do what? Find the other one, right? We can't just take purely what's given to us on the paper. We have to take it and use that to find the Ka or the Kb of how the ion is behaving. And then we run through a quick ice. And then that's it. I'm not going to do 6 right now because we just kind of talked about titrations for a moment, okay? Okay. Pull back out your packet. Look for... my joke of the day. Ah, great. Thanks, guys. Okay. I tried. I thought it was funny. Elephant cat. It's kind of old, but timeless. Okay, so find this piece of paper in your packet. I don't know if it's in the first or second line. Surprise. It's in the first one. It might be in the first packet. Okay, so I believe in you. I'm giving you 30 minutes to do 3 questions. Doesn't seem too bad, right? 10 minutes apiece. So you guys are going to approach with a partner 1, 3, and 10. Okay? And what you'll notice, you'll notice that there are little diagrams down here, stars and squares and triangles. That's going to help you really recognize your particulate diagrams once again. Because if you see, or if you're required to draw particulate diagrams, you should be able to do that appropriately. Okay? So 1, 3, and 10, work with a partner. And I would definitely use that little graph there to construct the graphs that it's asking you to graph. Questions? Thank you. If you have your little eye consent to you put in your face, or me having your face, I'll take that as well. Show your work, guys, okay? These are good, like, FRQ-based practices. Drew, do you have a copy? No? It's in the first packet. We can't find it. I can see that.
I was trying to see if I had any extra products, and I'm at a loss here. So you're at your name. I don't like it.
Yeah.
Just look, yeah, look how easy for it. It is maybe long. It was at the end.
I was also. Yeah.